Hello, my name is Caroline Johnson, and I will be presenting a paper titled When Your Fitness Tracker Betrays You, Quantifying the Predictability of Biometric Features Across Contexts. This is for the Fall of 2019 section of Cyber Physical Systems Security at the Georgia Institute of Technology. I would like to begin by acknowledging the writers of this paper, Simon Ebers, Giulio Lovisotto, Andrea Patane, Marta Kwiatkowska, Vincent Linders, and Ivan Martinovic, all from the University of Oxford in the United Kingdom. This paper was originally presented in the 2019 IEEE Symposium on Security and Privacy. Biometric data is becoming more and more mainstream as a source for authentication, as it is seen as more secure than standard passwords. Strong passwords require many strange characters, and a length often means greater security. Unfortunately, strong passwords are not friendly to the normal individual, and many people fall prone to using the same password for many accounts, or simply securing all of their accounts with a password of password. Additionally, by making a password easy to remember, it also makes it very easy for someone to hack. As such, biometric authentication is becoming much more common, as now nearly every phone features a thumbprint or retinal scanner for authentication. Though this may seem overkill, most phones hold access to nearly every other account an individual has, and they are often not authenticated within the device itself. However, as proven by many Mission Impossible and James Bond movies, fingerprints and retinal scans are not as foolproof as they would seem. In their place, the use of keystroke typing patterns and mouse movements have become the gold standard for biometric-based authentication. Unfortunately, these are prone to attacks as well. First, the attacker will record or otherwise obtain the biometric data, and second, they will either mimic that behavior themselves or train a robot to mimic it to the authentication system. This paper formalizes their topic into 3 research questions. The first is, how can attackers obtain biometric information without compromising the template on the authentication device? For instance, the Touch ID template on your iPhone is the recorded data on your fingerprint that the iPhone checks every time you authenticate. Is there a way that hackers could record that template without altering the Touch ID software such that the template is no longer viewed as secure? The second question asks, are context-specific changes in features systematic, and can they be predicted? To illustrate what they mean by context-specific, consider authentication based on how an individual walks. If a hacker were to record the individual walking on the street, their gait would likely be different than when they are walking in the authentication system. Is the difference in how the individual walks based on the context predictable? Lastly, does this predictability impact the security of biometric authentication? In order to answer these questions, the researchers looked at the individual features of biometrics and assigned them an unpredictability score based on their predictability across various contexts as previously described. If a biometric is unpredictable based on context, it is likely more secure. The researchers compared 5 biometrics in terms of their unpredictability: gait, or how people walk; touchscreen dynamics, which is how people use a touchscreen; ECG, which stands for electrocardiography, measuring the electrical activity of a heartbeat; eye movements; and mouse movements. To measure this, they recorded biometric data through a user study of 30 participants. In the threat model proposed by the authors, let's take gait data as an example. The victim uses gait to authenticate their smartphone, and they also wear a smartwatch that records their gait insecurely. Because of context, there is a difference in the gait used to authenticate and the gait recorded by the smartwatch. The adversary must learn how to transform the data from the smartwatch to fool the smartphone. To do this, they obtain smartphone and smartwatch data from a population that excludes the victim to determine how to transform the data, and then they apply that transformation function to the victim's smartwatch data to gain access to the smartphone. In summary, the attacker obtains biometric data from a context outside of authentication. They then determine the method of transforming that data to work in the context of authenticating. Finally, They replicate that transformed biometric data by either mimicking it themselves or by training a robot to mimic it, thereby thwarting the system's security and correctly authenticating within the system itself. Gait is the unique way in which individuals walk. Although the general way in which people walk is similar, there are slight variations in factors such as the size of the step, the speed of each step, and the pressure with which the foot meets the ground. Additionally, there are slight variations in gait between stepping with the left foot and right foot, and gait also varies between tasks such as walking and running. Because of these unique and complex features, gait is used as a biometric for being unique amongst individuals. Gait data is easily obtained from fitness trackers, as their accelerometer data is easily accessed through various APIs, with no permissions required. Touch dynamics are the ways in which individuals interact with touch screens. Typical interactions include tapping and swiping, but within those interactions are intricate variations in pressure, speed, and location. Each person taps and swipes on a touchscreen in slightly different ways, making it a simple yet effective biometric. Touch dynamics are easily recorded by creating a seemingly innocuous app or game that silently records how the users swipe, tap, and otherwise use their touchscreen. Electrocardiography is a measurement of the electrical impulses made with each beat of the human heart. While all heartbeats share similar characteristics, each heartbeat is slightly different. By measuring unique changes in the amplitude and period of the waves recorded in electrocardiography, there lies a unique signature and biometric for each individual. Computerized medical records are actually very prone to leakage or theft, which allows for obtaining electrocardiography data. Additionally, fitness trackers record electrocardiography signals and are also prone to attacks as described previously. When the human eye reacts to different stimuli, there are minute differences in those reactions between individuals. For instance, the rate and degree of pupil dilation or the speed and reactivity of an eye movement provide a unique biometric for each person. Many devices feature infrared sensors and cameras, and simply by hijacking a browser and silently recording the victim's eye movements, this data is easily obtained. In a similar fashion to the previously described biometrics, mouse movements are slightly different between individuals in terms of speed, reactivity, and pressure, to name a few features. By recording mouse movements, there is again a unique biometric signature for each individually. Similarly, mouse movements are easily recorded through browser hijacking and again, silently recording data on victims. In order to collect data for their research, the authors recorded data on 5 biometrics: gait, mouse movements, eye movements, touch dynamics, and electrocardiography, all by having 30 participants complete a series of tasks. The authors employed several standard techniques to avoid experimental bias. And to process the data, the authors utilized common practices for biometric data processing and feature extraction. For each participant, they gathered features in the source context and target context through different experiments. They then created a cross-context mapping to transform the source context into the corresponding target context. The result is a set of functions that would map features from source to target contexts. To evaluate the effectiveness of this mapping, they measured the prediction error by feature, or biometric. From there, they take a weighted average to aggregate the unpredictability score across all of the features. This score is not used to measure the success rate of attacks, but is instead used to compare different biometrics, with higher unpredictability indicating greater security. It is also used to identify vulnerable target contexts and to help with the selection and engineering of features to ensure higher levels of security. Let's dive a little deeper into the calculations behind that unpredictability score. The goal in one of these attacks is to convert the biometric data from the source context to the target context without any error. When that error is low, it would indicate that the biometric is easy to hack, or that the mapping from source to target is highly predictable. Additionally, when that error is high, it would indicate that the biometric is more secure, or that the mapping from source to target is less predictable. The unpredictability score, U, is thus equal to the error calculated in the attempted cross-context mapping. In technical terms, the unpredictability score U for each participant V and each biometric feature, G sub j, is equal to the error function in the cross-context mapping for that biometric feature, G sub j, and participant V. A high unpredictability score means that the mapping from source to target context was done with high error rates, indicating a secure biometric. A low unpredictability score means that the mapping from source to target contexts was done with a low error rate, indicating an insecure biometric. In an effort to reduce bias, the unpredictability score by feature is weighted using relative mutual information, or RMI. By comparing each data point to its neighbors and class neighbors, the authors determine a ranking for the mutual information between each data point. The unpredictability score for each feature is then weighted by the relative mutual information ranking to determine the overall weighted unpredictability score for each biometric. Formally, the relative mutual information score is represented by R, and the weighted unpredictability score, W sub V, is the sum of the error in the cross-context mapping, weighted by the relative mutual information ranking R, divided by the sum of the relative mutual information rankings. The typical features analyzed for touch dynamics are pressure, spatial use, speed, and acceleration. In order to gather data on touchscreen input, the authors created a smartphone application in which users would be provided two images to swipe between that were nearly identical but with subtle differences. When the participant identifies a difference, they are to tap it. In the background, the application is recording the touch dynamics employed by the participant. By swiping, they are able to record the pressure, spatial usage, speed, and acceleration, and similarly are able to do so when the participant taps the screen as well. To record data on electrocardiography, the authors need to be able to analyze the temporal features and amplitude of the curve reported by the electrocardiography monitors. The participants were wired into several electrocardiography monitors on their palms, a chest strap, a fitness monitor, and a smartphone device. When recording, these devices report several waves, though the most important features are their amplitude and the duration and spacing between their peaks. When these features are extracted from the recorded data, they prove to be unique between individuals, even though the overall pattern of the electrocardiography is similar among humans. To measure gait or walking style, the most important features to record are acceleration metrics from various locations on the body. The participant's gait was recorded by a smartphone on their arm, a smartphone in their hand, and a smartphone in their pocket. Additionally, the participants wore a smartwatch and a fitness tracker to record their gait. The experiment for electrocardiography and gait were done simultaneously, and while wearing all of the previously described sensors, the participants would take a short walk followed by a short run. The important features to record for eye movements are the pupil movements as well as the temporal and spatial features of the moving eye. Given a laptop with an eye tracker, the participants were to carry out 5 different activities: reading, writing, watching a movie trailer, browsing, and watching an educational video. The authors decided to include 2 videos in their experiments as the fast-paced scene changes of a movie trailer are likely to produce different eye movements than an educational video. Additionally, this experiment was done twice on each participant, once when the eye tracker was calibrated and once when it was uncalibrated. A calibrated eye tracker is simply one that has been trained to look at the eye movements of a specific user, and thus would provide clear, high-resolution results than an uncalibrated eye tracker. For mouse movements, the important features to consider are the curvature of the mouse strokes, as well as the speed and acceleration of the mouse. The participants were given a grid of rectangles and were asked to click on the rectangle that contains a picture. When the rectangle is clicked, the picture moves to a different rectangle and the process repeats. The experiment was performed twice on each participant, once with a mouse and once with a standard computer trackpad. To present the data, the authors needed to settle on what contexts would serve as sources of data and which contexts would be the target of an attack. For the gait biometric, the target context is walking with a phone in your pocket, while the sources are walking or running with the recorder in your hand. For the touch biometric, the target is a mid-quality level phone, while the sources are high-end or low-end quality phones. For the electrocardiography biometric, the target is the NIMI band, which uses electrocardiography as an authenticator, while the sources are other electrocardiography sensors located at various places on the body. The eye movement biometric uses calibrated tasks as the target, with uncalibrated tasks being the source. Finally, for the mouse, a standard mouse is the target, while a trackpad is the source. Each biometric context was given an unpredictability score as previously described. A high score indicates the difficulty in mapping data from a source context to the data context required for authentication, and thus means a biometric with a higher authentication security. Overall, the weighted average unpredictability score for the 5 biometrics was as follows. For electrocardiography, an unpredictability score of 0.09. For eye movements, an unpredictability score of 0.08. For mouse movements, an unpredictability score of 0.07. For touch dynamics, an unpredictability score of 0.08. For gait, an unpredictability score of 0.15. For more information about the unpredictability score of each sub-feature for each biometric, I refer you to the paper itself, linked both at the beginning and the end of this presentation. Of the 5 biometrics, gait performed the best, indicating that by placing the sensor elsewhere on the body, the gait information varies dramatically, making it difficult to transform that data to the template needed to authenticate. The next most unpredictable was the electrocardiography measurement, with eye movements, mouse movements, and touch dynamics falling as the least predictable. For electrocardiography, the feature that most impacted the unpredictability score was the location of the sensor used as the source. Sensors located near each other, for instance on the hand and wrist, would provide the most similar readings. This highlights that using hand-based sensors for authentication is highly susceptible to hacking, as data from similar contexts is easily obtained. For eye movements, regardless of whether the authentication is based on pupils, speed, or acceleration, the movements themselves are highly predictable between participants. If a hacker can reproduce something even remotely similar to what is used for authentication, they will easily be able to replicate and compromise the authentication system. The touch dynamic experiment detailed a low predictability score, as from phone to phone, adjustments based on screen size are highly predictable. The authors recommend that for this reason, stroke duration should be removed as an authentication feature. Additionally, they mention that higher-end phones have higher quality sensors and are thus more secure for use in authentication systems. For mouse movements, the authors note that regardless of the features analyzed, the unpredictability score is very low. The trackpad collected data with very low sensitivity, and the manner in which the mouse was used was not significantly distinctive between subjects. This does highlight that using more precise and more higher resolution sensors will likely thwart attacks from lower quality data sources. In conclusion, the authors created an unpredictability score as a way of comparing biometric systems, identifying vulnerable target contexts, and selecting and engineering the most secure biometric features for authentication. Their results showed that electrocardiography and gait are the most unpredictable of the 5 biometrics analyzed, proving more secure than touch dynamics, mouse movements, or eye movements. Additionally, by looking at the specific features of various contexts for collecting biometric data, the authors were able to prove that better quality sensors increase a biometric authentication system's overall security. To answer the title question, are our fitness trackers betraying us? While gait and electrocardiography proved to be the most unpredictable, the simplicity in obtaining data from fitness trackers, combined with the contextual similarity of the data recorded by the trackers and the data used for similar authentication features, is certainly a sort of betrayal. Thank you.